Now, I would like to share some special design for RF capacitors. Usually, for ideal capacitor, we hope it is linear and with very high Q, and also it can generate huge capacitance per unit area, right? It's really unlucky that no capacitor fits such kind of requirements. For all those parallel place capacitor, just like me, metal, or polymetal, all of them, even though they are linear, but they can only generate comparatively low capacitance per area. Even though they are high Q, their quality factor is high, but their capacitance doesn't scale with the feature size. It means, according to process evolution, the capacitance per area cannot be increased correspondingly. Okay, and what is the definition for capacitor linearity? According to the equation, the most fundamental equation for capacitor, Q equals CV, it means the charges and the terminal voltage, actually they have such kind of linear dependence. How about the MOS capacitor? Yeah, MOSFET, it means active capacitor. Actually, it's quite nonlinear. Why? As I mentioned already, the Q versus V look like that. Wow, is highly nonlinear because it is far away from such kind of linear dependence, right? However, it can generate much higher capacitance per unit area, but the quality factor is not so good. Also, it is temperature sensitive, and also it required good enough DC bias to bias here or there. You can get variant capacitance. If you bias your capacitor here over there, then it really means that the effective capacitance will become really small, right? So for all those two major kinds of capacitors, they have their own pros and cons. The authors from maybe Stanford or Berkeley University, they would like to create a new one to combine all the benefits of those two kinds of capacitors. All right, what's that? It means they would like to create something new for capacitor with good linearity, high quality factor, but also generate large capacitance per area. It will be very good for RF applications. What they created is called fractal capacitors. But why? Simply because they would like to apply some mathematics called fractal geometry, 碎形几何, for capacitor layout. Wow, it's really amazing. They are not only good at analog IC design layout, but also very good at mathematics. It's quite special because most of the analog IC designers comparatively are not so good at digital or mathematics. They are quite talented. Anyway, anyhow, the main idea for such kind of new capacitor called fractal capacitor, they would like to apply to depend only on lateral flux because it has much better matching property than the vertical flux. Okay, these are lateral or horizontal flux. On the contrary, this and that, they are vertical flux. For matching, actually, lateral one is much better than the vertical one. Why? Simply because TSMC, UMC, for process evolution, they pay a lot of attention to the width of the wires and also the spacing between wires. That's it. They didn't pay much attention to the gap between metal layers. Why? If they try to reduce the gap between the metal layers, then it means it will cause substantial parasitic capacitance between metal lines, right? It is really bad for wires, for routings. So they just let it be. It means no much improvement, no much enhancement between the gaps, for the gaps between the metal layers. They don't need to spend too much time on that. It means no much improvement, and for never mind for matching or for scaling down. They simply don't care. Okay, this is the reason why lateral flux is much better than vertical flux in matching, and it can be scaled down with process evolution, as I mentioned moments ago. The other issue you need to be very careful is how about the flux between the bottom metal and the substrate. Actually, it only causes the parasitic capacitance between the substrate. It is really harmful for our circuit operation. So we hope to make it as less as possible. All right. That is the scenario, that is the logic thinking behind such kind of creation for fractal capacitors. Later, I will explain in which way they can depend, the capacitance depends much more on lateral flux than vertical one. And how can they reduce such kind of parasitic flux? It is really important for the property of the new capacitor. 不能集合哈，这组作者因是我们在对 Berkeley 啊，对 Stanford 这种系出名门的大学出来的了哈。那他们厉害之处就是在于说，他们不只对类比 IC 设计布局非常非常的在行，他们对数学也非常非常的厉害。所以呢，他们就想用一组很神奇的数学，称作碎形几何，来干嘛？来创造出这一种非常神奇的那个电容布局了哈。目的最简单的就是讲，因要想办法提高电容对那个水平电场、水平那个电力线啊、电通量的那个依赖程度了哈。那要大幅的删减电容对垂直电场、垂直电力线的那个依赖性啊。那更有趣的是，他们也可以顺便消减最底层的那个板子跟基底中间的这个电力线。意思是什么？对基底的杂散成分可以被大幅的消减，这个对我们电路或尤其是对高频电对 RF 电路的运作有非常棒的那个帮忙。So allow me to show this. According to scaling of the process, you can see not only the width of the knives will be reduced, also the spacing between them will be reduced. And as I mentioned, more bending. The more bending, the more charges or the more energies you can store inside the gap. It means the more capacitance you can create for more bending flux. Okay? In this way, the capacitance will be increased according to process evolution, because not only the gap, the spacing will be reduced, but also you will get more bending for such kind of fringing effect. All right, and then for such kind of vertical flux versus lateral flux, you can see from the very beginning, this is for parallel plate capacitor. You have the top plate, the bottom plate. You depends very much on the vertical flux. All right. So if you cut it into two halves, then the lateral flux will show up, and also the vertical flux will be reduced. Then you can cut it again. You can cut one big capacitor into two, then into 4, then into 8, all the way to the smallest line width and the smallest spacing. In this way, we can say that the impact of the vertical flux will be reduced very much, and the impact of the lateral flux will be increased substantially on the capacitance, right? Even better is that according to such kind of flux, you can see, for example, this is positive, that is negative, right? Positive here, negative there. As I mentioned, according to process evolution, we can reduce the width of each line. It means what? In the middle, if you reduce the width, the middle flux will also be reduced. And how about the boundary flux? Actually, you can see from its neighbors, from the positive neighbor to the negative neighbor. Okay, from the positive neighbor 9 to the negative 9. Okay, from here to there and other positive wire. Okay, so in this way, if you reduce the width very much, I promise you the vertical flux in the middle will be reduced almost to 0. So it means that to the end, all the flux will be bended back from the positive terminal to the negative terminal. They don't go down to the substrate or injected from the substrate to the negative terminal. In this way, we can reduce the bottom plate capacitance very, very much. It is really good for our circuit operation, especially for RF circuit operation. All right. And what is such kind of how to implement such kind of fractal geometry? Actually, through the help of Koch curve. From the beginning, for example, you have a square, right? But you need to replace each square with such kind of generator. For each one, it is replaced with this, with this, with that, with that. Then you will have a new one according to such kind of fractal geometry, right? You can achieve the first order fractal geometry, then go further. What do I mean for going further? Very simple. Again, you can replace each line, each segment with such kind of generator. You can make the final layout even more fractal than before. That is the logic thinking. 啊，别人去实现这种所谓的碎形几何，简单的哈。譬如说你都开始几的些正方形的布局，然后你把每一边呢都用这种启动器把它启动图形把它给取代掉 ，generate。OK 好啊，所以讲四边拢总用这种来取代，按就变这种拿形，对不？啊，你也开始继续把布落去啊，就讲你可以继续啊，每一小节又都用同样的东西去取代，啊，有加 C 啦，那就会乱成一团。Okay, for such kind of fractal layout pattern, you will see even from A to C, from the beginning, if it is positive, that is negative, where can you find the lateral flux? Only at the boundary here, right? So after the first generation, with the help of coach curve, you can generate something like this. It means the boundary between the positive and the negative will be substantially increased from the original one. Alright, it means the lateral flux will be increased substantially from A to C. Then you can do the same thing. Alright, I mean to replace each segment with the generator again, you can see how much boundary you can create through such kind of coach curve generation. Just do it again and again. To the final stage, you can increase, you can generate much more capacitance per area. That is the scenario. However, if you would like to make it, if you would like to do it by your own hands, sorry for that. That is really hard to do such kind of fractal layout. So the authors, they are such talented. They make it through the help of EDA tools. It means they are not only good at IC design layout, but also at mathematics and EDA tools. Without all those talent ideas, I don't think you can make it. So forget about it. I don't recommend you to follow their design. Okay, I mean, I strongly recommend you not to do any layout according to fractal geometry. Okay, actually, to my memory, the same authors, they create another one with much simpler in layout. That is what I recommend you. That is the so-called vertical parallel plate capacitor, or nowadays we call it MOM. All right, that is the capacitor type I would like to recommend all of you to follow. Anyhow, you can see the total capacitance over the parallel plate. I mean, for the same area, if you compare such kind of fractal capacitor to parallel plate capacitor, you can see how much enhancement you can get according to such kind of horizontal spacing. The smaller, the better. You can see they can be enhanced. I mean, the capacitance per area through the help of fractal geometry. You can see more than 10 times enhancement can be achieved. However, the more fractal, the better, right? What is D? D is called fractal dimension, 碎形维度. Anyway, it's hard to say. Then I would like to explain it through the help of good enough plot. You can see for fractal dimension, the right one is larger or better than the left. That's it. So it means what? The more you apply through such kind of coach curve generation, the more dimension for fractal geometry, the larger D you can achieve. That's it. And the larger D means what? The more capacitance per area you can generate compared to parallel plate capacitor. Anyway, the authors, they are not only talking, but doing. They try to implement such kind of fractal capacitor by themselves. Again, through the help of EDA tools, they didn't do such kind of dirty layout by their own hands. Sorry for that, it is almost impossible. This is the micro photo for their fractal capacitor, and this is the much simplified capacitor model according to their experiment. Anyhow, Here are some kind of brief conclusion for such kind of flat talk capacitor. First of all, it is linear, at least much linear than before, than the parallel plate capacitor, and also the bottom plate capacitance is much lower than before. It means the parasitic capacitance to the substrate actually is reduced very, very much. And also the density can be improved with process scaling, right? With better process, you can reduce the spacing even further. Then you can see more and more enhancement in the capacitance per area you can achieve. That is a good idea. But my brief conclusion is it is really hard for regular humankind. If you are not as talented as the authors, forget about such kind of fractal capacitor. What you can play, please forget about it. I will show you the next one. Okay? The next capacitor actually will fully focus on the vertical parallel plate capacitor instead of the horizontal one. That's it. Anyhow, again, the authors would like to enhance the capacitance according to lateral field. Okay, they would like to enhance very, very much. They would like to enhance very, very much the efficiency of such kind of lateral electrical field. Why such kind of capacitor is important? Simply because it is really good for not only analog applications, but especially for RF applications. In the past, as I mentioned for previous chapter, for previous paper, we have such kind of very old style horizontal parallel plate capacitor. It depends very, very much on vertical flux. It is not scaled with the process, and also the accuracy or the matching is really poor. Okay, then they try to focus on different layout pattern of the capacitor. For example, one of them is called parallel wires. We have such kind of parallel wires. Then for such kind of bird view for the layout, two-dimensional layout view, you can see they depends very much on such kind of lateral flux, very much, right? It is good. However, between layers, you still have such kind of vertical flux. So you can see for parallel wires, the capacitance depends on not only vertical flux, but also lateral flux. Yeah, that's it. We hope we can focus on lateral flux, and we don't want the capacitance to be dependent on vertical flux. All right, let's go further. That is some kind of brief introduction for such kind of metal lines. Again, for the vertical gap between the wires, actually, it is not scaled down with the process evolution. Only the horizontal spacing will be scaled. Okay, so hopefully we will focus on this, on horizontal flux instead of vertical flux. So how to make it? We can go further. So ideally, if you can make the horizontal parallel plate stand up to become vertical one, then congratulations, all the flux will be lateral instead of vertical. 你若有这个这个水平平板架，互伊徛起来，你就是真厉害哈！所有的那个电力线全部都会变成水平的，而不是垂直的。OK， that is what we would like to do for the even newer capacitor. This is what I can show you. Yeah. For the authors, they call such kind of capacitor as vertical parallel plate structure, VPP. Nowadays, we call it MOP, metal oxide metal. Yeah, you can see we don't have such kind of real parallel plate. Only according to the horizontal line, or according to the horizontal direction, we have, for example, metal 2, metal 1, or poly 2, poly 1. How about the vertical plate? We don't have real vertical plate, but we can emulate it. For example, you have all those metal 9 connected with vias. It will be good enough, okay, to simulate or emulate such kind of horizontal plate. 好，咱其实无真正迄个垂直平板咱敢若有迄水平平板，要安怎模拟水平平板？最简单的啊，你就甲介意迄个金属线从metal 啊一直往上走，然后中间用一大堆的 vias 把它连在一起啊，那么小港啊，伊的意思小港啊，咱也是模拟，还是讲模仿那个水平平板无真正的垂直平板，但是我们有这个仿真的那个垂直平板 ，OK， 模拟一下In this way, you can see where will be the flux. Only lateral one. That is very good. And is there any vertical flux? Almost not. Why? You may say, hey, to the bottom. Yeah, to the bottom. But I told you already, if this is positive, that is negative, according to the very narrow line and very narrow spacing, very small spacing. Most of the electrical line will be bended back from positive to negative. Okay? From positive to negative here, from positive to negative there. Almost no electrical line will penetrate into the substrate or inject it from the substrate. So it really means that the parasitic capacitance between the bottom lines and the substrate, almost nothing. Okay? It will be very close to zero. It is really good for circuit or RF operations. Alright, to make it even better, we have such kind of vertical bar structure. You can see, this is the top view. Wow, many of the flux in this direction, along y direction, or along x direction, but no flux along z direction, right? So it means no vertical flux, only lateral flux. But compared to this one, maybe only in x direction, right? And for vertical bars, in both x and y direction. Never mind. For all those, I mean, for VPP and VB, actually, they don't have any flux along z-axis. It means they don't have any kind of vertical flux. It is what we need, right? To enhance the matching property and also to make it scaled with the process evolution. Bingo, that is what we want. So if you would like to compete with the authors, yeah, you can have any other kind of new structure just like this. It is called modified vertical bar structure, or even some along this direction, the others along the other direction, or parallel lines. In theory, the best is 3D cubes. Okay, but what is the problem? How can you connect all of them if they are already with the smallest size? No way. There isn't any line to connect all those blue cubes or all those purple cubes. Nowhere, right? So for 3D cubes, it is only good in theory, but it is totally not possible for real layout, for real implementation. Forget about it. All right. And how about parallel wires? Again, it has lateral flux, but also vertical flux. This is no good for matching. It is also not scaled with process evolution. So compare with our vertical bars or vertical parallel plate, this is no good. Oh, I forgot to mention that in theory, vertical bars is better than vertical parallel plate, right? But what is the problem with vertical bars? Just think about it. How to connect all the blue bars and how to connect all the purple bars. Do you have any idea? Huh? No, right? All right. Allow me to tell you the truth. Usually, you need the bottom plate end. You need to sacrifice the bottom plate to connect, for example, the blue bars, and then the top plate to connect all those purple bars. That's it. So for 0.80 micron process, we have only M1 all the way to M6, right? M1 for blue bars, M6 for purple bars. So actually, you have only M2 to M5, only 4 layers out of 6 are realizable for vertical bars. On the contrary, here you can apply all of them from M1 to M6. In theory, all of them can be used to compose such kind of vertical parallel plate capacitor. So usually VPP can generate more capacitance than VB per area. Got it? The other drawback of VB is if I collect with the help of the top metal to collect the purple bars or the bottom to collect the green bars, blah, blah, blah. Some of the problem is, again, I would like to have such kind of vertical view for you. That is the top bar, right? Then you collect all those purple bars, and then the bottom one to collect all the green bars, right? What will go wrong? This area and that area. For example, this is positive, that is negative. Then you still have some vertical flux here, 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 and there. Not all of them depends on vertical flux. It will cause some problem for vertical bars. Why? Again, vertical flux is no good for matching. Okay, and also it doesn't scale with process evolution. To the end of the paper, I will show you the property of V bar of vertical bars actually is not so good as vertical parallel plate. The authors prove it by experiments. Believe it or not, with solid proof from the experiments, you guys had better believe it. VPP is better than VB. Okay, let's go further. The authors have quite many crazy ideas for layout pattern. One is called woven structure, without via or with via quasi-fractal capacitor. Because as I mentioned, they belong to the same group. So they still concern something about fractal geometry. So they would like to do something very similar to that. So they have such kind of quasi fractal capacitor structure A, B, C, and D, blah 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 blah. Anyway, this is some kind of capacitor limits according to physics, fundamental physics. The theoretical limit look like this, but in practice, we have no way to achieve it. So we have another semi-empirical upper bound. Empirical means according to our experience, right? So semi-empirical upper bound means more practical than the ideal one. The new equation actually has such kind of modification term. For your reference, don't ask me. I admitted already from the very beginning. I'm only good at IC design and layout, but I'm not so good at mathematics. If you are good at mathematics, please help me to explain why this one is more practical than that. And for such kind of semi-empirical equation, why you need this term? Don't ask me. And I'm not any kind of expert on this. All right? If you are interested, maybe you can Google online by yourself, or maybe write some emails to ask help from the authors. It's up to you, not me. All right? Let's go further. From the simulation, you will see the blue line actually is for the theoretical upper bound. You can see no capacitor type can be very close to the theoretical limit. So it means forget about such kind of theoretical limit. And then how about the semi-empirical upper bound? 半径跟方程式的哈。That is the green line here. Oh, you can see some capacitor is very close to such kind of semi-empirical upper bound, and the other one is very close here. All right. So which is very close to the semi-empirical upper bound? That is the horizontal parallel plate. Whenever the line width is so huge, it means for very old processes, HPP, horizontal parallel plate, is good enough. So you can see for old processes, you have only such kind of horizontal parallel plate capacitor. That is the key. But for the past, how about right now? Here, right? We hope our process is already here. Then which one is the best? This one. Which is that? Vertical bar in theory. And who is the second best? The light blue one, right? For the light blue line, that is the vertical parallel plate. So in theory, for new processes, vertical bar is better than VPP. However, that is only in theory. In practice, I told you already, you need to sacrifice the top and the bottom plates to collect all the vertical bars. So usually, the vertical bar is worse than vertical parallel plate. Okay? So there is a big difference between the practice and the theory. The practical condition is much different from the ideal condition. Now, anyway, allow me to show you this. For vertical parallel plate, you have only one direction for such kind of horizontal flux. Lateral flux, I mean. Our vertical bars, I mentioned already, it has two directions along X and Y, both for such kind of vertical bars. Anyhow, For both capacitors, they don't have such kind of vertical flux. Very good for matching. All right, they don't have those, so it means they are very good for matching, and also they can be scaled with the process evolution. And how about the others? All of them have such kind of vertical flux. Yeah, vertical flux. So none of them will be good for matching, and none of them will be scaled exactly with process evolution. Then allow me to show you such kind of comparison among them for ideal value. Okay, you can see vertical bar is the best. Never mentioned about it is quite close to the theoretical limit, even closer to such kind of semi-empirical limit, but only in theory. Again, for practice, you need to sacrifice 2 places, right? Then you will become far away, even further away than the vertical parallel plate. If you don't believe it, no worries. A moment later, I will show you the truth with the experiments from the authors. Here are some kind of measurement results. For 3 metal layer, you can see the authors tried to implement 3 kind of capacitors. One is VPP, parallel wire, and then the traditional horizontal parallel plate capacitor. After measurement, you can see VPP is almost the best. According to the capacitance density, it is the best. How about the average capacitance? It is the best. Okay? Yeah, many of them. The only trouble maybe the breakdown voltage. The breakdown voltage for HVP is higher than VPP. Why? Because the gap, the spacing between the 2 plates, actually they are larger than the horizontal spacing, right? I explained already. So the larger spacing means the more you can tolerate for such kind of breakdown voltage. But it is good. It is good, but also bad. Because the spacing is larger, it means they can generate much less capacitance per area, right? If you focus on breakdown voltage, actually for VPP, more than 300 volts is good enough, even for IF transceiver. No worries about that. Nowadays, for our IF transceiver, I think they operate at most more than 10 volts. Sometimes even only 4 volts. So they don't need to tolerate hundreds of volts for breakdown. No worries, nothing will happen for that. Okay, and then they use better process with 7 metal layers to implement again VPP and the traditional horizontal parallel plate, but also vertical bars, because they can sacrifice 2 out of 7. So totally they have 5 metal layers for VB. And then let's have a look at the results. Those for 1 picofarad, I think large enough for many of the applications. Anyway, anyhow, you can see VPP dominates almost everything. From the capacitor density, the area smaller, the area the better, right? And also the standard deviation is the smallest. You can see the matching property for the VPP or even VB. Yeah, you can see who is the best. VPP. Why? It depends only on lateral flux. And how about HPP? The traditional one, it only focuses on vertical flux. It's really bad for matching. And how about the VB? I told you already, some of the vertical flux still exists, right? So it is harmful for matching. The poor matching means the more standard deviation. That's it. So it is a solid proof, a strong proof for vertical parallel plate. No. It is a solid proof that lateral flux is much better than vertical flux for matching. Okay? Yeah. Anyway, the quality factor is the best. The only weakness is again the breakdown voltage for VPP, but it's still more than 100. Good enough, even for RF operations. Then they try to implement for all those three capacitors for even larger capacitors, 10 picofarad, as I mentioned. Then again, you can see vertical parallel plate generate almost the best performance. Never mind for what kind of parameter you can send. And again, the only weakness is the breakdown voltage, but it's still higher than 100 volts. Good enough. Okay, then I would like to show you the deviation. Oh, if you compare all those three capacitors, you can see how much variation for the traditional one. See, positive, negative 6%. Okay, and how about the best vertical parallel plate? Don't tell me it's 0. No. Because for each grid, it is 2%, right? So I guess here for VPP, how much is that? I guess positive, negative 1%. Okay, and how about parallel wires? Actually, positive, negative, maybe 3 or 2%. Okay. Anyhow, again, it is a solid proof. Not only for VPP is much better than all the others for matching. It also proves that horizontal flux or lateral flux is much better than vertical flux for matching. Okay? Finally, we come to such kind of admittance plot. What is admittance? Usually you guys focus on impedance. Impedance means 1 over SC, S means J omega, omega means 2 pi F. So for impedance, the magnitude is reduced with higher frequency, right? So what is admittance? Admittance is the reverse of impedance. So you have J2 pi FC. It means what? The magnitude of admittance for capacitor is proportional to the frequency. If you plot admittance versus frequency, it needs to be a straight line, just like VPP, right? So here, the linear portion means everybody is ideal for capacitance. But if you have a look at the traditional one, you will see it gets big trouble here. The line is never be linear. The curve is never be linear, right? So it means what? Its property is not so ideal for capacitance. Even worse is this. After the resonance frequency, it goes down instead of going up, right? Here, it has some kind of capacitance property. There, according to the going down property, the admittance is reduced as the frequency is increased. It means that it looks like an inductor here instead of a capacitor. Wow, it's really terrible. Beyond the frequency, beyond the resonance frequency, such kind of horizontal parallel plate capacitor will become some kind of inductor. Will your circuit operate normally? No. Your capacitor becomes inductor. Maybe your inductor also becomes capacitor. It will be a disaster for your circuit operation, right? So who can provide you the widest operation range for capacitor? VPP. VPP is the best. You can see the linear region extend all the way to almost here. How much? More than 20 gigahertz. And even for current 5G operation, the most I guess is only around 5 gigahertz, right? And what is the next generation? Years ago, we will proceed to 7 gigahertz, and other years ago to 10 gigahertz, blah, 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 blah. So it means what? Maybe such kind of vertical parallel plate capacitor can survive even for your son or grandsons. Why not? So please focus on VPP instead of all the others. You may be curious, how about the best in theory? I mean, vertical bars capacitor. You can see the curve is bended around here. See? So it is no good for more than 10 gigahertz. But VPP stands still from DC all the way to more than 20 gigahertz. It means for frequency consent, VPP is still better. I cannot say much better, but it is still better than VB. Bingo! That is the power of knowledge. I read such kind of paper more than maybe 20 years ago when I taught the class, when I taught IC layout in Hsinchu. All the TSMC guys, they didn't have any idea about such kind of VPP. In that era, the mainstream process is 0.18 micron process. After my teaching, they went back to check the property of VPP. Finally, for 19 nanometer process, TSMC provide MUM to IC designers. Wow. From 0.18 to 0.13, then to maybe 0.11, and then 19 nanometers. So it means three generations beyond 0.18. Then TSMC can provide such kind of good idea, such kind of good capacitor for you guys. Again, if TSMC guys read this article earlier than me, then more likely they would like to provide such kind of MUM capacitor for IC designers earlier than 90 nanometer. Maybe. Okay. This is the end of this chapter. Hopefully, you know everything you need for capacitor layout, and this will be good for your third homework. Thank you.